potential V. If you include the potential V, then how does it affect? So that we have seen, and then one can put the Schrodinger equation in a final form, where we saw that the Hamiltonian operator has a role to play when it acts on the given particular psi function. It gives some expectation values to you. Then we came across a concept of the probability interpretation, because after all, what we are interested is to see what is the probability of finding the particle in the given system. So one of the ways suggested by Max Born, and that was to take up the complex conjugate of the function, so psi star into sine, or you say modulus of psi square. So that gives you the probability density. And when you multiply the probability density, then it gives you the probability of finding the particle in the given region. So you have this probability of finding the particle, and it has to be equal to 1 according to statistical mechanics. So we also observe that the sign must approach to 0 as you go towards minus infinity and plus infinity. And then we came across this normalization condition, where we got this normalization constant. And then we moved on to the concept of the probability current density, which was more meaningful than the probability density, because we said that probability actually changes as the wave progresses over a period of time. So if you want to understand more in a better way, the probability current density has to be interpreted. So for that, we performed some mathematical operations on the Schrodinger equation, and we came across a term which was actually approaching to 0 as r tends to infinity and minus infinity, meaning by that your whole probability density is actually constant. So in order to say that the probability density is constant, we have to have this equation, where we define this equation by a parameter called probability current density, which is J equal to IH bar upon 2m into psi del psi star minus psi star del psi. And it is also called the equation of continuity. You know this one, when you substitute this value in the previous equation over here, so we find that we have the time derivative of the probability plus we have a time derivative of the probability plus this particular gradient of the probability and density. So this is called equation of continuity. And when you compare it with hydrodynamics and electrodynamics, you will see the similar equation of continuity. And in quantum mechanical sense, it is also called the conservation of the quantum mechanical probability. It is a conservation of quantum mechanical probability. And then we saw the meaning of the expectation value. So how we can use this concept of the probability. We can use this concept of probability to find out the expectation value of some parameter. So we have some position coordinate, let's say r, and we want to find out its expectation value. Then simply what we do is that we multiply that position coordinate by the probability, and it is simply sandwiching that particular parameter between the complex conjugate of psi and its psi and its complex conjugate psi star. So that is the expectation value. And then we came across some quantum mechanical analog for classical expression from the Schrodinger equation. So we use the Schrodinger equation. 2.47 is your Schrodinger equation, this one above over here, and then you multiply it by psi star, and you integrate it from minus infinity to plus infinity on both the sides of this equation. Then we come across a conclusion that this is nothing but your total energy is equal to the kinetic energy plus the potential energy. So that is nothing but the quantum analog of the classical energy expression. And then we saw that we can find out the expectation value of any dynamical variable. So the way to find is simply put that parameter in between the functions and its complex conjugate and integrate it from minus infinity to plus infinity. And if the given function is not normalized, then we divide it by the normalization integral. Generally, this integral is equal to 1, but if in the given problem, if the integral is not normalized, then we have to follow the normalization procedure. So this is what we have seen so far. And what we have seen so far is the time-dependent Schrodinger equation, this one. So this is your time-dependent Schrodinger equation. And now what we want to see is the time-independent Schrodinger equation. Okay. So that is what we want to begin today. So in order to describe the time-independent Schrodinger equation, we must separate the wave function. So if your wave function is separated into two parameters, where psi, which is dependent on both the position and the time, is separated into two functions. Now psi depends on position separately, and it depends on the time separately. So I have given, I have used two different parameters for that psi r and psi phi t. So if you substitute this expression in your equation 2.47, 2.47 is nothing but our Schrodinger's equation. So that is, let me just set. Yeah, so in this equation, what we want to do is that we want to substitute psi rt equal to this function psi and phi, two separate functions. So let me do this in separate sheet. So for that, yeah. So for this, if I want to substitute psi rt, so you have psi rt is equal to psi r and phi as a function of t, and the equation is this. So in this equation, I'm substituting psi equal to that particular expression. So this is only the derivative with respect to time. So you will have phi common out of this particular equation. So you will have phi t into ih bar del phi by del t. So this one over here. Okay. And on the other hand, you have this Laplacian operator, which is a derivative with respect to position. So we simply just substitute. So I will write down this as Hamiltonian h for the time being is equal to. So I have this operator h, and on the right hand side you have this psi, which is now replaced by psi into phi. So this is what we are doing. And then it says dividing throughout by the psi and phi, this multiple. So if you divide on both the side by this multiple, so let me just divide it. So you have psi r phi t, and you will have psi and phi t. So I'm dividing on both the side by this parameter. So this will get cancelled over here. Okay. And sorry. So this is not going to be phi.
अरे सर चलेगा क्या? हेलो हेलो। अरे अरे सर चलेगा लगता है। हेलो, कोई है कि मेरा आवाज बंद हो गया?
हाँ हाँ, आवाज आ रही है मान। रुक जा
हाँ,
सर, शायद आते होंगे।
हेलो।
हाँ
यस
सर।
सर, यस सर।
ओके, हाँ। एक्चुअली यहाँ पे इंटरनेट का थोड़ा इश्यू था।
हाँ हाँ, वो यहाँ डिपार्टमेंट में है पहले से भी इशू।
राइट, या ओके, सो आई थिंक थोड़ा मुझे फिर से आई विल हैव टू स्टार्ट. So you just tell me from where it was lost. So I'll just share the screen. And I was talking about the time independent Schrodinger equation. So कहाँ से कटा हुआ था? So if somebody can guide me, I can move from there.
सर वन नोट में आप लिख रहे थे ना, उसमें शायद एक या दो लाइन लिखी थी, उसके बाद चिपक गया था।
Okay. Okay, thank you. Okay, so what we were doing was that so we said that we want to separate this wave function into two parameters, and then we substituted this whole into equation 2.47. So 2.47 is nothing but our time dependent Schrodinger equation. So that is somewhere, let me say, IH bar del psi by del t is equal to so there was this Hamiltonian operator, and then you had psi. That is our Schrodinger equation in 3-dimension format. And psi over here is as a function of r and t on both the sides. So what we were doing, that we wanted to substitute this thing in this equation. So in this equation, when you substitute psi equal to psi as a function of r and into phi as a function of t, then you have psi which is taken common out because we are differentiating with respect to time. So you will have only del phi by del t. And on the right hand side, you just simply replace psi rt by these two functions now. And psi gets cancelled, and you will have IH bar 1 upon phi t del phi by del t is equal to, and over here your phi will be get cancelled because Hamiltonian is an operator which includes this time dependence Laplacian. So now, because this is a function of time, this is the function of position. Sorry, not time dependent. It is a position dependent operator. This is del square by del x square. So this is a position dependent operator. So it will first operate on this function psi. So what we will write, that 1 upon psi r into h into psi r. So phi gets cancelled over here. So this is what we should be getting. This is what we should be getting over here. Okay, where I have written this whole expression as a Hamiltonian. Okay, now if we see on both the side, this is only a function of time t. This is only a function of position r. Okay, so both are a different differential equations which are independent from each other. They both are independent from each other, and therefore I can say that both the sides should be equal to some constant. Okay, because the t and r both are independent variable, so both sides, left hand side as well as this right hand side, so that should be equal to some constant. Okay, so this is like saying something that if x is equal to y, then they must be equal to some particular value, let's say 5, so that you have x equal to 5 and y equal to 5. Okay, so for the moment we are assuming that that constant is something, let us say it is a constant e, capital E. Okay, this is just an assumption, and we will see later on why we are taking E as a constant. Okay, so at the moment it is just a constant, it is not nothing like energy, or it doesn't mean anything, it is just a constant. So if you substitute the right hand side or left hand side both equal to this constant E in this expression, then what do we get? That d phi by dt is equal to, so this whole expression goes on the right hand side. Okay, let me just write over here. So if this is equal to E, then d phi by dt is equal to 5 times E divided by IH bar. Okay, 5 times E divided by IH bar. Now IH bar, so it is written as minus 1 upon I. Okay, so this function, this is 1 upon I over here. I mean, it will be something like IH bar. So इसको अपन अब ऊपर ले जाएंगे तो क्या हो जाएगा, माइनस आई हो जाएगा. दिस इज गोइंग टू माइनस आई बिकॉज आई स्क्वायर इक्वल टू -1, सो आई इक्वल टू -1 upon I. So 1/5 d phi by dt equal to minus IE upon h bar. ठीक है, and the right hand side, this side, so this is simple, so equal to E. So E into psi, that is what simply it is written over here, left hand side as it is. Okay, so we get two equations now. So if we look at this first equation, so this is simple enough to solve, and if you apply this method of separation of variables, so ye kya, this is nothing like these simple equations which is generally what we see, dy upon y is equal to some constant k into dt, है ना. This is phi की जगह मैंने y लिखा है यहाँ पे, instead of phi I am writing y. So if you have this type of equation, then if you take the integral on both the side, तो क्या हो जाएगा, ln of y equal to kt plus c prime and y equal to c into e raised to kt. ठीक है, where c is equal to this e raised to power c prime. C is the constant, in short, it is nothing but a constant. So the solution of this equation is going to be y equal to c into e to the power kt. Now I will replace this y by phi, which I have assumed initially, and k is equal to minus IE upon h bar. Okay, k equal to minus IE upon h bar. So what do I get? Phi equal to c into e to the power minus IE h bar, IET upon h bar. So phi equal to c exponential of minus IET upon h bar. Okay, so that is the solution of this particular equation. All right, c is your constant, and this second equation, so this is your time independent Schrodinger equation. Okay, because we don't see any time parameter in this equation. All right, so this is your time independent Schrodinger equation, and because this is only a amplitude related equation, है ना, because this is only the position dependent. जो आपका wave है तो उसका position जो भी है position, so that represents the amplitude. So this is also called the amplitude equation. All right, so this determines the amplitude of the equation, so it is also called amplitude equation. Now let us substitute this value phi into our initial assumption, where we separated the whole psi function into two parts. So in this equation I am replacing phi by this value. So your psi is equal to sine r exponential of this function, where c is included in the normalization constant for this function. Now, because after all, when you solve this whole equation, so this will also have some expression multiplied by parameter of r, and यहाँ पे you will also get some constant c prime. So this c is also included in the expression for this. All right. Now, if we want to see that why we have taken this constant e, or why we did not take any other constant, है ना. You can take any parameter, but we have taken E. So the reason is that if you take the equation 2.72, so ये जो हमारा equation है, or just take up this function sine RT, and if you differentiate by time, if you differentiate by time with respect to time and you multiply it by IH bar, तो क्या हो जाएगा IH bar del sine RT by del T. So because we know that E corresponds to the parameter IH bar del by del T. So this whole expression is going to be equal to E into sine. All right. So in this equation, if you multiply by sine star from the left, and then you integrate from minus infinity to plus infinity. So integral minus infinity to plus infinity into sine star. Now I am separating IH bar del by del T and sine as a function of R and T dt. On the right hand side, now this is going to be equal to sine star into sine minus infinity to plus infinity dt. So this is going to be equal to 1, okay, according to the probability. So probability is going to be equal to 1. So that is going to be equal to E. Okay. Now if we see, interestingly, this integral over here, this represents nothing but the expectation value of this whole parameter. So that's why that's the way we find the expectation value, that we put the given parameter between the sine and its complex conjugate sine star, and you integrate it from minus infinity to plus infinity. So this whole equation corresponds to the expectation value of E, and we know that this is nothing but your energy operator. Okay, this is nothing but your energy operator. So expectation value of the energy operator, so वो क्या देगा? It gives nothing but energy. As simple as that. So that is why this taking this constant E justifies by taking this. I mean, ये जो हमने what we said, that this both left and right hand side are equal to some constant, and we are taking it to be some constant E. And the reason we have chosen E is that it is nothing but the expectation value of the energy operator. Okay, and you can also understand the same thing by simply understanding the fact that this is nothing but the Hamiltonian. This is nothing but the Hamiltonian. So Hamiltonian क्या होता है? जैसे हमने अभी डिस्कस किया था, ये आप क्लासिकल मैकेनिज्म में भी पढ़ेंगे कि it is nothing but the your operator, which is T plus V, that is your kinetic energy plus potential energy. And whenever you operate this Hamiltonian operator on any function, so it has to give you the energy of the system. Generally, it is represented by a cap because it is an operator. So H cap is operating on function psi, which is giving you the energy. All right. So that's why we are taking this constant to be equal to E. यहाँ पे जो हमने constant दिया था कि दोनों तरफ equal है, so that a constant is equal to E. So that is all about Schrodinger's time-dependent equation. And now the last topic for this unit that we are seeing is that what are the admissibility conditions for the given wave function. So we have discussed so many things that the given wave function, what is the wave function? We started from the concept of the wave packet. So we said that for a given particle, we can assign a wave packet like this, and it is going minus infinity to infinity. Then we came across this exponential of ik dot r minus omega t expression लिया था हमने, and from that we obtained the Schrodinger equation, both time dependent and time independent. But what exactly the character of this function sine is? I mean, what should be the conditions for the given function sine? So it says that for a wave function to be acceptable, these two things, what are they? Sine and gradient of sine. So they should be, or in fact it says it must be finite single valued and continuous at all points in the space. Again, why is it so? See, we have seen all these parameters, the probability density. So probability density क्या था? Okay, भाई, that was like your sine star into sine. Okay, that was the probability density. And when you multiply it by this, integrate it from minus infinity to plus infinity, and then it gives you the normalization procedure. I mean normalization integral. Okay, and then we came across and then we saw that this probability also changes as the wave function changes. So we should have some unified concept to describe the probability. So that is probability current density. So probability current density, what was that? That was J R J as a function of R and T. That was equal to IH bar upon 2m into bracket. We had sine del sine star minus sine star del sine. All right, that was the probability current density. So if we see all these parameters, what we are observing, the integration of sine is included in this particular integral, and you are also having this gradient of sine star or what, gradient of sine. So in order for these definitions to be valid, mathematically what one should have is that both these parameters, sine and gradient of sine, they must be finite, they must be single value. That means it has a single value at the given position, the given point, and it must be continuous at all points in the space. All right, so this is a bit of mathematical definition. This you might have seen in your first year course mathematics, when you are discussing about vector algebra, or sorry, vector calculus में शायद पढ़ा होगा. So that operator del, so that operator del, when you're defining, when you generally take this operator del with some function phi, so gradient of phi, then you have the divergence of phi, okay, or I mean any vector, or you have curl del cross given particular vector, whatever. So if you see all the definitions of this, so it has the one common thing which says that the given function should be finite, it should be single valued, and it should be continuous at all points. So this is a very simple definition of the admissibility condition for the given wave functions. This type of questions generally also they are asked in if you go for some competitive exams like SLATE or something, state level eligibility test. There are certain, sometimes, I mean not all the time, but sometimes it has been asked in past. NET में नहीं पूछते इतना simple सा, because it's just a definition. But in SLATE I have seen this type of things that you ask. What is the admissibility condition for a given wave function in terms of quantum mechanics? So these are the answers for that. That the function sine and del sine should be finite, single valued, and continuous at all points in space. Okay, so that completes these admissibility conditions. And I think let us do some examples. We should do some examples so that it should complete this whole experience of going through all these exercises that we have done so far. The time independent Schrodinger equation, time dependent Schrodinger equation, probability current density, expectation value, normalization condition, all the topics that we have gone through so far. So we will take some examples now, and we will see how to solve those. Okay, so if we see the first example, the question is that normalize the wave function where capital A and small a are constants over the domain minus infinity to plus infinity. Okay, it's a very simple question. It says normalize the wave function. Okay, so what is the normalization integral? So we have this normalization integral, that sine star sine d tau integral from minus infinity to infinity is equal to 1. Okay, this is the normalization integral. So let us do this, and we should find out the integral of this function. So okay, let me see. So So what is the function? I'll just write down. So sine x, okay. Example 2.8. Sine x is equal to a exponential minus ax square. So capital A exponential of minus ax square. So this is the wave function, and we want to normalize this. So simply, so this normalization integral, and this is just in one dimension. It is only in x dimension. So over here we take dx integral. All right. So minus infinity to infinity into sine star. So sine star, if you take the complex conjugate of this, it is going to be the same exponential of minus excuse me, minus ax square into sine again. So it will be the same thing. It is going to be the same thing. So let me just write down exponential of minus ax square into dx is equal to 1. Okay. So this is going to be equal to a square. I'm taking it out because a, capital A, is constant. And you have this integral minus infinity to infinity exponential of minus 2ax square dx equal to 1. Okay. Now over here, one needs to know what are the integral values of this standard integral, है ना. इसका जो standard equation मतलब ये होता है, formula होता है. So one needs to know that. So it is like if you have e to the power minus kx square, and we are taking an integral e to the power minus infinity to plus infinity to dx. So the value of this integral is nothing but under root of pi by k. Okay. So this is a standard integral. However, if you want to derive it, you can derive also, but it then becomes long mathematics, which we do not want to do in that. I mean, considering the fact that this is not that complex example given to you, it may be something like 2 marks question or something. So that is a very short question, and in that sense, you simply just plug in the value of this integral. So the value of that integral is going to be equal to pi under root of pi by 2a equal to 1. So this should give you a is equal to 2a upon pi whole raised to 1 by 4. All right. So normalization karna, which means what? We want to find out this constant. And because it is said this one is constant. So iska value jo hai, that we will just plug in over here. So that is rewriting the wave function sine x, which is 2a by pi to 1 by 4 into exponential of minus ax square. Ax square. That is answer. Yeah, answer है. So that is how we normalize. All right. So let's do this similar example so that you will get a better idea. So second example, which says a particle which is constrained to move along x-axis in the domain 0 to L. All right. So particle का जो domain है वो हमको दिया है. यहाँ पे था it was minus infinity to plus infinity. Over here the domain is 0 to L. It has a wave function sine x equal to this, okay, where n is an integer. Okay. Normalize the wave function and evaluate the expectation value of its momentum. Okay. So यहाँ पे we haven't given any constant, but as we have seen previously that this normalization integral का मतलब ये कैसे रहता है? It is simply it is the same thing. It is simply just multiplying this by n square, some normalization constant n. Okay, so we just simply multiply this value over here and over here and so if you follow that trend, then so we'll follow the same thing. ये जो condition है, ठीक है? So you have now you have the integral 0 to L. Integral is from 0 to L sine star sine. Again, it is in one dimension dx n square is equal to 1. So this is going to be n square integral 0 to L and sine star sine. Okay, again, it is only a real function. It is the complex. I mean, it does not have any imaginary part. So if you take the complex conjugate, it will be the same function. So simply sine square हो जाएगा. तो sine square n pi x by L, n pi x by L dx equal to 1. Okay, now let us solve this. Let us solve this. Okay, so you do it by yourself and solve this and see what value you are getting for n. n का वैल्यू आपको क्या मिलता है? ठीक है, इसको बस इंटीग्रल करना है. तो कैसे करना है वो आप अभी सोचिए.
सर
हाँ जी.
सर अंडर रूट हाफ आएगा शायद. तो
अंडर रूट हाफ
नहीं, अंडर 2/L हाफ बराबर
अंडर रूट 2 by L.
2/L.
Okay. Okay, so let us all verify that we are getting this answer. If majority are getting this, that means it should be correct, or it has to be. So capital N is equal to under root of 2 by L. ना इसको बस आपको split करना है. This is sin square theta, which is 1 minus cos 2 theta by 2, so 1 minus cos 2 n by x by L whole divided by 2. And then you can separately integrate both the terms. सबका आंसर आ रहा है n equal to 2 by L, and if that is the case, then our wave function sin x should have the form sin n pi x by L multiplied by this normalization constant, so sin n pi x by L. Okay, if this is true, then this should be the normalized wave function. So those who have got the answer, you can just reply.
Yes, I got it.
Yes, sir.
Oh, okay. Okay, so I hope everybody is getting this. Right. So I think that this should be the correct answer, and it is correct answer. So sine is normalized to this format. And so we have one more question in that, which says that evaluate the expectation value of its momentum. ठीक है, so you want to calculate the expectation value. तो अभी हमने we just now we have seen that expectation value कैसे निकलती है. So we simply put the value of that particular operator. मतलब यहाँ पे अभी momentum लिखा है, momentum का जो operator है, so we plug in it between these two, sin star sin. All right, and उसका integral जो अभी निकला, whatever we will evaluate, that will be the normalized. Okay, and it is already normalized, so we don't, because remember when we discussed, I said that we need to normalize it. Okay, previous slide में होगा anyway. So we generally need to normalize it by dividing it by integral sin star sin. Okay, that is how we do it. But we have already normalized this. तो जो ऊपर का इंटीग्रल है minus infinity to infinity sin star, and if you have some operator a sin theta, so you will have this integral as an expectation value. So we want to find out the expectation value of the momentum. So what should we do? In that case, we are finding the expectation value of the momentum. So we are writing in this bracket px is equal to minus infinity to plus infinity, and over here we have the limit 0 to L sin star. So इसका जो भी star है, so that is simply okay. So okay, let me just write down first. So 2 by L sin n by x by L sin star into px. Okay. Now px I can write down as a momentum operator, which is minus ih bar del by del x. Okay, that is px, and multiplied by sin. So it will be the same. ये पूरा का पूरा यहाँ पे same होगा. So 2 by L into sin n by x by L. So this is going to be equal to this is going to be equal to 2 by L constant outside 0 to L. This is going to be sin square n pi x by L dx. And oh, sorry, we have this. Okay, let's delete this. We have this operator. What we need to do, so minus ih bar, okay, let's just write it, minus 2 ih bar upon L outside del by del x of this function. So you have sin n by x by L into the differentiation of this. So sin का हो जाएगा cos n by x by L into the differentiation of this, which is n pi by L. Okay, if you take this common out, minus 2 n ih bar pi divided by L square integral 0 to L. So this is sine into cos. So we can put it as a 2 sine theta. I mean sine 2 theta. Sine 2 theta is equal to sine theta cos theta. So this is going to be sine 2 times n pi x by L divided by 2 dx. All right. So if you integrate this whole, you will see that this will simply be equal to 0. Yeah, because it's a sine function है ये. So sine 0 0 हो जाएगा. Sorry, you will have cos function, and this is an odd function. ठीक है, तो ये 0 हो जाएगा. So you do it. You first integrate this, पूरा इंटीग्रल निकालो. It should be equal to 0. क्योंकि साइन का जो इंटीग्रल है cos हो जाएगा, and when you will write down these values, तो दोनों तरफ 1 हो जाएगा, 1 minus 1 हो जाएगा, it will be 0. So just verify that you are getting your answer to be equal to 0. So I hope your answers are your answer is equal to 0.
Yes, sir.
Okay. तो सबका आंसर देखो 0 होना चाहिए, ठीक है. So it is very interesting to see that you see that expectation value of the momentum is actually 0. And it's very interesting to see because it says that particle is constrained to move along the x-axis in the domain 0 to L. So it is moving, but the expectation value of the momentum is 0. Yeah, it's very, very interesting. We'll see these things later on also. What actually this means. How is it possible? When you will go through more detailed concepts. Okay, so I hope everybody is getting this answer equal to 0. Okay, next example is 2.9. Give mathematical representation of a spherical wave. Okay, spherical wave का mathematical representation है, which is traveling outward from a point. तो पहले तो mathematical representation देना है. तो अच्छा, what I will do, I will give you the mathematical representation. You calculate its probability current density. ठीक है. तो mathematical representation simply given by a wave which is traveling outward, a over r into e to the power I k r. Okay, so that is a mathematical representation. So it is written in polar coordinates. So that is how it looks like, where a is your constant. Okay, and we know k is the wave vector. K is the wave. K is equal to 2 pi phi lambda. So that is wave vector. Now it says evaluate probability current density. So probability current density, ये वाला. So we need to evaluate this thing, this function j as a function of r d. So we need to find this thing. So let's do it. So I have given you this mathematical representation. Now you calculate the probability current density. ठीक है ना. तो वो कैसे होगा? J as a function of t is equal to, so we have IH bar upon 2m. So we have IH bar upon 2m into sine del sine star minus sine star del sine. Okay, so over here you just replace the wave function by this one, e to the power ikr into a by r. So a by r is constant, है ना? So you do it on your own, ठीक है? a by r is constant and gradient of psi star. So psi star क्या हो जाएगा? a by r. It is a complex conjugate of this function. So that is going to be e to the power minus ikr. Okay, the gradient of e to the power minus ikr minus psi star. अच्छा, यहाँ पे भी होगा a by r into, ये दोनों के बीच में हो जाएगा e to the power ikr because you have the whole function in sine. तो यहाँ पे भी होगा a by r into, यहाँ पे साइन स्टार है, so you will have e to the power minus ikr into the gradient of a by r, gradient of sine. So sine is a by r into the power ikr. So you have to just simplify this thing. ठीक है, इसको simplify कीजिए, so you should get the value of the probability current density. So one thing is common that you can take out from both. Now that is a into a square IH bar upon 2m into a square into the bracket. So you have to now take the integral, the differential of this operator. ठीक है ना? This is all the is on this is only in one dimension, so you will just take del by del r. तो यहाँ पे दो फंक्शन है, it is del by del r of e to the power minus I k r अपन r. ये जो है पूरा the gradient of this whole function है ना? a तो कॉमन निकाल लिया यहाँ पे, तो ये जो पूरा फंक्शन है it is going to be like this. So this is, you know, integration by part, differentiation by part. You have to take इसको अगर ऐसे differential, if I write down, तो पहले 1 upon r को concentrate किया and I will differentiate e to the power minus I k r into minus I k, इसका differentiation. And then I will keep e to the power minus I k r constant, differentiation of 1 upon r, which is minus 1 over r square. Okay, and then you have to just simplify this thing. इसको simplify करके you have to substitute in this one. Similarly यहाँ पे भी होगा So what answer you are getting in this bracket? So it's the same function over here where you simply sign is different. So two terms will be cancelled. Now when you will expand this whole multiplication term, तो यहाँ से दो टर्म है वो कैंसिल हो जाएंगे. So two terms will be cancelled and you will get two terms and both are same. So you got the answer for this? You should get minus 2ik upon r square in this bracket. You will have two terms over minus ik upon r square minus ik upon r square. So it will be minus 2 times ik upon r square. So you will have 2 gets cancelled and this will be I square equal to minus 1. So h bar k a square divided by mr square. So that should be your probability current density. H bar k a square upon mr square. So everybody is getting this answer?
Yes, sir.
Okay. So I hope all of you are getting these answers. If you are not getting, then it's fine. You just practice it more. You should get this. This answer is correct. Okay, so I think we should stop here, and there are, I think, a couple of more examples, but we'll see it next time. ठीक है, okay. Thank you for your attention, and have a good day. Yes, if you have any questions, you can ask.
Oh, sir. No, sir.
Okay, so Thank you.